This video will walk you through the steps as to how to graph a simple rational function. Rational functions are basically functions that involve fractions. So we're going to take a look at today how they are graphed, because they do look a little bit different than some of the other types of graphing you've learned earlier in the year. So rational functions are going to graph as hyperbola, which basically are going to look like graphs that are broken apart into two or more pieces that are called branches. Most of the ones that you're going to deal with are broken into two pieces. You will see a couple of graphs in this chapter that break apart into three pieces. Now, these graphs break apart because there are certain values that if you were to plug them into the function, they come up as undefined, or depending if you have exponents involved, come up as imaginary. Those cases, we are going to see things that we call asymptotes. Asymptotes basically are these invisible lines that we put on our graph as dotted lines to basically say these values don't work. So part of graphing these is to understand where the asymptotes are going to fall. So where we are going to have these invisible lines as barriers, if you will, to the graph. We're going to figure out how those work, and then we'll also figure out how to plot the graph, and then identify what we call the domain and range. So let's talk about our two types of asymptotes. We have the possibility of vertical and horizontal asymptotes. So we're going to talk about how to find both of these things based on the way these functions are set up. So let's talk about the vertical asymptote. Vertical asymptote can easily be found by taking the denominator of your rational function and setting it equal to 0. So if you look at our function here, we are going to set the denominator x plus 2 equal to 0 and simply solve for x. So I would have an asymptote at x equals negative 2. What that basically means is if I plug negative 2 into the function, it's going to give me, basically, if I work through the math, negative 4 over 0. You can't divide by 0, which means you're not going to get a real number solution. It won't be, you can't see that on a graph if it's not real. So we are going to go ahead and show that on the graph by making a vertical line, because again, vertical asymptote, it's going to be a vertical line where x is negative 2. So we make a dotted line to show that barrier. We have another type of asymptote called the horizontal asymptote. So you will learn in another video how to find horizontal asymptotes in a few different ways. Based on the way that these functions are set up, these are actually the easiest to find the horizontal asymptote, because all you have to look at, if you look at the function that's up above, you have a fraction, and then you have something just kind of randomly, an integer just tacked on at the end. In this case, minus 1. Because of the way this is set up, our horizontal asymptote is simply whatever value is being added or subtracted to the fraction itself. In this case, it's negative 1. So our horizontal asymptote is going to be at y equals negative 1. You'll learn again, there's other rules in terms of finding horizontal asymptotes when the fractions are all set up in different ways, and you'll learn again about that a little bit later. But in this case, we got a horizontal asymptote, y equals negative 1. I'm going to make a horizontal line where y is negative 1. And we have that set up. Now, once you have the asymptotes, we're going to go ahead and plot the graph. So your graphing calculator is going to be really important here. Otherwise, you're going to be plugging and chugging in a ton of values. So when you use your graphing calculator, now I can't necessarily split screen this right here, but with your graphing calculator, you want to punch it in like you've done all the other types of graphing we've done so far this year. Take a look at the graph so you see what it should potentially look like, and then go to your table of values. When you go to your table of values, the best way to find the points that you need is to basically look for the x value where the vertical asymptote is. So the vertical asymptote is at x equals negative 2. If you scroll through your table and find where x is negative 2, it'll say the y value is an error. That makes sense because that's our asymptote line. That's that invisible line. There is no y value that spits out. Using that value will kind of give you a barometer as to what points you should use around it. So my suggestion is use that asymptote value, so in this case negative 2, as like the middle point of your xy table. You want to pull enough points, because you'll see with these graphs, if you look in the notes, these graphs bend. They have very sharp bends to them. You want to have enough points that you can clearly see where the bend occurs. You can pull an infinite amount of points just like any other graph. My suggestion would be from where you see the vertical asymptote point where x is negative 2, I would pull from your xy table the first, I'd say, 4 numbers above and the first 4 numbers below that x value. That should be enough to plot your graph. So in this case, I'm going to use the 4 values that come before -2, the 4 values that come after -2. And that, again, should be enough. If you want to plot 5 or 6, again, that'll give you an even more accurate sketch. But again, I would go with, in this case, pull 4 from each side, and that'll definitely give you enough points. So again, all you're going to do here is copy your XY table from your graphing calculator. And once you do that, all you're going to do is then plot all of your points as accurate as you can. You're going to get a lot of decimal answers when you do this, or a lot of fractions, depending on how your calculator is set up. But ultimately, you're going to get a bunch of points here. So you'll see as you continue to go further and further away from the asymptote point, if you will, the y values are going to get a lot closer to each other. Because what happens in these graphs is that they make these sharp turns towards the asymptotes, and they start getting really, really close to them. They'll infinitely approach the asymptote, but never quite hit it. That's the whole point of these lines. So you'll see when you graph here what I'm talking about. So let's go ahead and plot that here real quick. So here's the first part of my graph. So again, to kind of match it from my graphing calculator, this kind of makes sense. It's going to make really sharp turns. So I have my bend. It's going to make a sharp turn to the left, and it'll make a sharp turn upward. Then I have the second part of my graph. So we'll put that down here. And again, it starts downward, and it makes a sharp turn right. And again, if you look at your graphing calculator, now what you'll see on the graphing calculator is that it looks like it flattens out. And because of how the calculator is zoomed in, it's going to look like that. But if you zoom in really, really close and infinitely zoom in, it will constantly be approaching that invisible line. So there's going to be some direction to it. It's just going to look really flat on your calculator because it can only compute so much. So we have our graph. Great. Now we're going to use that graph to identify the domain and the range. Now, you learned in Algebra 1 about domain and range simply as domain is your x values, range is your y. If all your domains are different, you have a function. Wonderful. We're going to do a little bit more with that here in Algebra 2, and if you move on to trig and pre-calc, you'll definitely do more with how to identify domains and ranges. We're going to use something called interval notation to identify what's the domain and what's the range. So, domain, again, is your x values. That's the basic of it. So how far does my graph go left to how far does my graph go on the right? If you take a look at your graph, so we look at the whole graph. So even though there's 2 pieces, it's one whole graph. So if I look at the graph here, I want to know how far left it's going to go. If you pay close attention here, we've got an arrow that points left from the branch in the top left corner here. The fact that it points left means it's going to go infinitely in the left direction. So if it goes infinitely left, that means it will approach negative infinity. That's where it's starting from, okay? So we go negative infinity as our leftmost, not point, but it's far left as it goes. We don't know when it stops. We just know it's infinite in the negative direction. Now we need to figure out how far from the left towards the right. How far can I go before I hit a break in the graph? So if I go infinitely left all the way towards my right, you'll notice I start making that bend, and it sharply bends as we approach when x equals -2. So again, going left to right here, we basically write down where the break occurs. Okay, so we know it's not going to hit -2, but we know it's going to approach -2. We put the value where the break is going to occur. However, if I were to get over that asymptote, so basically just kind of think of it as like hopping over a fence. If I were to hop over that fence of x equals -2, all of a sudden this graph can go even further to the right. So what we do here is we have to account for that other piece. We use this little U that stands for union. It's kind of like a connector. This allows me to connect multiple sets of domains together. This is why we use interval notation, because it's a lot easier to write than it is any other way. So what we're going to do here is say, okay, if I start back again past -2, and I go even further to my right, you notice there's an arrow pointing right all the way to infinity. If I look at that here, that means my domain will extend all the way to positive infinity because it extends infinitely to the right because of the way the arrow is pointing. So my domain would be written as negative infinity to -2. with that little u for union connected to -2 to positive infinity. Basically, what you'll see with most of these hyperbola is that they range from negative to positive infinity. This will not be the case for all these other graphs that we're doing, but for a lot of the hyperbola, they'll typically extend infinitely left, infinitely right. The trick is to figure out where is the break when I go left to right. That break is where our domain will either stop or start again, because that's the value we are approaching. So that's why we use -2 there, because again, left to right, we have that asymptote line at -2. Range is the same idea, except range involves your y values. That means we're going from down to up. So if I go from down to up, I want to look how low does this graph go. So again, I look at the graph in totality here. I see an arrow pointing downward. The fact that I've got an arrow of one of my branches pointing downward means it's going to go all the way to negative infinity. So that's where it's going to start from. Now, I want to look at the graph and start going up, 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 up. How far up does my graph go before I hit a break? Well, it goes up, and then I see that asymptote at y equals -1. So that means my graph is going to approach up to -1. But again, if I hop over that asymptote line at -1, I can start all over again, and it's going to go upward. As you can see from the top of the graph, there's an arrow pointing up to positive infinity. So I basically write the range the same way as the domain, except I'm looking at it from down to up. I'm looking at it from a vertical scale. We point downward, so it's going to go to negative infinity. Our asymptote is at -1, so basically that's where our graph is going to stop and then start again. Use that little u for the union as a union. It connects the two pieces together. We start again at -1, just over that, and then it goes all the way to positive infinity. There's a couple other little pieces you'll learn about how to write the interval notation, but again, this is what we're going to use for these type of functions, radical functions, etc., as we move forward. So that's kind of a recap here and how you go ahead and graph these type of problems. So just to recap in short, to find the vertical asymptote, take the denominator, set it equal to 0. That's going to be the case no matter what type of rational function that we do. Horizontal asymptote in these type of problems where you have a fraction plus or minus an integer, you just pull that integer that's being added or subtracted. There are other rules you're going to learn. You'll get to them later. Graph your function. That's probably the easiest thing for all of you to do. Graph everything using your graphing calculator. Just got to make sure you enter stuff right. Account for your domain and range. Domain, again, your x values from left to right. Your range values are from y, going from the lowest to the highest. And we're going to write them using this interval notation. So that's kind of your recap here on how to graph a rational function.